Hi, my name is Miguel Nicolelis. I'm a professor of neurobiology and director of the Center for Neuroengineering at Duke University. I'm here today to announce a discovery that we made here at our center and in collaboration with researchers at the Edmund and Lily Safra International Institute of Neuroscience of Natal. This discovery is a very interesting advancement of the field of brain-machine interfaces. And what I'm going to do today is to describe briefly what we did. In this first slide, I just present to you guys the general scheme of a brain-machine interface. And as you can see, classically, we use electrodes to read signals from the brain and transmit to devices. These are robots or virtual avatars or electronic gizmos that can be controlled directly by these brain signals. So this is the classical design of how we have been doing this research for the last 15 years, research that was pioneered here at the Center for Neuroengineering at Duke University. But what I'm going to show to you today is a complete different approach to this research, and this is the first report of a brain-to-brain interface. Yeah, you heard it right, a brain-to-brain interface. What we are reporting in a paper that is being published this week in Scientific Report, a journal of the Nature family, is that we were able to transmit brain-derived information from one rat to another and basically got this pair of animals collaborating to solve tactile and motor tasks. And that's what some of these images that I'm going to present to you describe in great detail. So initially, you can see in this slide the setup where we did all these experiments. You know, there's a behavior box where the first animal is located, and this animal is called the encoder because he's the one who does all the work. He's basically using his forepaws or his whiskers to perform either a motor or a tactile discrimination task. And while he's doing that, we are monitoring its behavior and recording the brain activity that is being produced by this animal's brain and transmitting in real time all these electrical signals to a second animal that is called the decoder. Well, this animal has the lucky job of not having to do anything for getting a reward. The only thing it has to do is to receive this brain activity into its own brain and then decode the pattern of information that the encoder has generated and indicate to us through behavior what it is that the first animal has discovered out there in the environment. So if the decoder gets it right, both animals get a nice juicy reward. And that's what they want. And that's how they collaborate to actually get this job done. So let me go ahead and introduce to you the first task that we use to test the performance of this brain-to-brain interface in rodents. Here you see in the next slide, encoder animal waiting for a light stimulus that tells the animal which of two levers he has to press to get a little bit of a water sip. And the light says either press left or the right lever. So when the animal gets the light and is about to press the lever, we record the activity, electrical activity from lots of cells in the motor cortex of this animal and instantaneously transmit this information through the brain of a second animal that is in another box and cannot see the light and cannot see what the first animal is doing. This is the decoder, and he's receiving this information through very tiny little pulses of electrical activity that are delivered to the homologous part of the brain that the encoder is using to solve the task. So as the decoder gets this information and basically decodes the brain pattern originated in the encoder's brain, it responds to us behaviorally by pressing one or the other lever to tell us that he got it right or not. And what we discover is that in 70% of the times, this decoder actually can get the task right without even seeing the light, just by decoding the brain pattern that the encoder donated to it. Well, when he gets it right, there is a signal that goes back to the behavior box where the encoder is and allows the encoder to get an extra reward. So they basically collaborate. Funny enough, what we've found as these animals learn to operate this brain-to-brain interface working together is that if the decoder gets it wrong, since the encoder cannot get the second part of the reward, it doesn't like that. So what it does for the next trial is to clean up its brain activity to make it smoother and cleaner and make the behavior even smoother than it was before, so that it makes it easier in the next trial for the decoder to get it right. And invariably, the decoder gets it right. So by the time the decoder gets it right, the encoder gets the supplemental reward, and then it goes back to the original pattern of behavior and the original brain signal. So that was a big surprise, and is the proof that these guys are collaborated. Even though they don't know that there is another animal in another box doing the task, we virtually created a biological computer that is interacting to find a solution heuristically. Well, this is a little movie that shows to you what I just described. I'm going to play it, you can watch, and I'm going to just go you play by play, what happens in this. So you see now the two animals in two different behavior boxes, and we have one trial now where the encoder sees a light that refers to the left bar. It goes there and presses the bar and gets its reward. Well, now the brain signal of this animal is being transmitted to the decoder, who doesn't have an indication of the lights because they're both on. So at this point, the decoder presses the correct lever, gets the reward, and the encoder gets a supplemental reward. So this is another trial showing on the right lever, the light showed up, the animal got it, the encoder is transmitting the information to the decoder is now decoding the message, press the right bar, and gets the reward. So they are collaborating. They are doing a communication through a brain-to-brain interface. Well, in the next slide, I show to you another task that we use to demonstrate how well this communication can happen. This is a task the rats love to do it because they have to use their facial whiskers to judge the diameter of an aperture. And that's how rats escape from cats, because they can measure the hole and see instantaneously whether they can go through. They can run through to basically escape the predator. Well, you can see a rat is the same rat doing two different discriminations of a narrow aperture in the left on the wide aperture on the right. And as you can see, immediately after they touch the edges of the bars that define the aperture, they come out and they are already turning the body to indicate to us what is the diameter. If it's a narrow, they go to the left. If they're wide, they go to the right. Well, we put an encoder doing this task, and as you saw before, as the encoder was using its whiskers to discriminate this bar, we basically recorded the brain activity from the tactile cortex that underlies the decision of this animal, and we broadcast this signal to another animal, a decoder, that was receiving this message through electrical stimulation of the homologous part of its brain, the somatosensory or tactile cortex. To our surprise, the decoder didn't need to touch anything with its whiskers, but it was in 65% of the time correct in telling us what was the diameter of an aperture that it never touched, because all the information that he used to do the discrimination was coming from the brain of another animal, the encoder, which got a supplemental reward every time the decoder got it right. So this is just a graph to show you that the performance of these animals using a brain-to-brain interface is above chance level in both the motor and the tactile task that I mentioned to you. This is, the first block of data shows how well the encoder performs each task, and it's close to 100%. They become very good. And this is how the second bar shows how the decoder performs each one of these tasks and is way above chance. And they are doing that just by decoding brain patterns generated by the encoder. So another thing that was very fascinating to find out is represented in this next graph. This next slide basically shows that if I stimulate the whiskers of the encoder's face as expected, the neurons in the somatosensory or tactile cortex of the encoder respond to that mechanical stimulation. That's expected because that's the part of the brain that represents the whiskers. If I go to the decoder brain, the same thing happens. If I touch the animal's whiskers, the decoder's whiskers, the neurons in the decoder's somatosensory or tactile cortex respond to the stimulation. That's also expected. What was not expected is that after practicing with this brain-to-brain interface for a month or so, when I now touch the whiskers of the encoder, the decoder's brain responds to these whiskers, in addition to responding to the animal's own whiskers. So somehow over this practice, we are able to create in the decoder's brain a representation in the somatosensor tactile cortex of the facial hair of another animal, in this case the encoder. So the brain-to-brain interaction made the brain of the decoder create a representation of a body of a different animal and superimpose that representation on top of the animal's own body map that exists in its brain. So to finalize these studies, in collaboration with our colleagues at the Edmund and Lily Safra International Institute of Neuroscience in Natal, we did a transcontinental transmission of brain-derived signals to prove that we could get this brain-to-brain communication working, even though an encoder would be in the northeast coast of Brazil, in the city of Natal, in the Edmund and Lily Safra International Institute of Neuroscience in Natal, and the decoder would be here at Duke University waiting for its partner to broadcast its brain activity, describing what was the aperture of a hole that the encoder was touching in the equator in the northeast coast of Brazil. And even though there was a delay in the internet transmission, both animals collaborate as if they were next door to each other, demonstrating that this mode of communication can be implemented at a distance. And in fact, instead of only two animals, one in Brazil and one in the United States, we could have lots of animals in different parts of the planet just exchanging information, as if they were in the same laboratory next to each other. So overall, this work shows that we have created a new way of animal communication and a new way to make these animals collaborate to solve a task that, when they interact via brain-to-brain interface, may even generate an emergent behavior that you didn't expect to see when these animals were separated and not exchanging information. So that suggests to us that perhaps we're just showing a proof of principle of a new way of computing, an analog organic-based computer that is computing in a non-Turing fashion, that is different from all the computers that we know that we use in our daily lives. And this is a very exciting future line of research that will open many doors, not only for brain-machine interfaces in terms of rehabilitation, but potentially for something in the very distant future that I like to call the brain net, a way in which we would be able to communicate just by thinking. Thank you very much.